Hi everyone. Today we're going to be looking at the concept of differentiability, which is just a way of talking about whether a function has a derivative at a given point. So if I can take the derivative at a given point, I say a function is differentiable at that point. If it doesn't have a derivative, we say it's not differentiable. So we're going to look today and see about how we figure out whether a function is differentiable at a point. So the first thing we're going to talk about is one-sided derivatives. And we know that since a derivative is a limit, we can look at one-sided derivatives just like we look at one-sided limits. So we're going to talk about the right-hand and left-hand derivative. So the right-hand derivative of a function at a point A is defined as the limit as x approaches A from the right of f of x minus f of a over x minus a. Now remember, that derivative is really just the slope of the tangent. So if I look at a specific value, I want to look what's happening at x equals negative 2. So I'm going to look at what happens as a limit as x approaches negative 2 from the right of f of x minus f of negative 2 over x minus a negative 2 or x plus 2. So again, I know what I'm really talking about here is the slope of the tangent at x equals negative 2. So at this point, I can consider, if I just sketch it in, tangent's going to look something like that. So I can tell by that slope, that's going to be a negative number. I don't know exactly what that number is, but I know it's going to be negative. Okay, likewise, I can look at the left-hand derivative of a function. At point A is just the limit as x approaches A from the left of f of x minus f of a over x minus a. So in this case, again, I'm going to look at what's happening at negative 2. I'm going to look at the limit as x approaches, negative 2 from the left of f of x minus f of negative 2 all over x plus 2. Now here, this is just linear, so that tangent is going to be the same linear function here. And so that slope is obviously positive, so that's going to be a positive number. So I can see in this example, my left-hand and right-hand derivatives are not the same. Now, we will only have a derivative at a point if the limit as x approaches A from the left of f of x minus f of a over x minus a is equal to the limit as x approaches A from the right of f of x minus f of a over x minus a. So in other words, it is only that derivative will only exist if my left-hand and right-hand derivatives are the same. So I can see from the work we did here that at x equals negative 2, I do not have a derivative. And so what we say, based on this, we would say that our function, I'm going to call it f of x, is not differentiable. Hopefully you can read that there. F of x is not differentiable at x equals negative 2 because those left-hand and right-hand derivatives are not the same. Okay, so just again to kind of reinforce some of the terminology here, we say that a function is only differentiable at a point if the left-hand derivative is equal to the right-hand derivative at the point. Okay, so differentiability is just talking about the derivatives. So we're going to look at some graphs and some types of functions to figure out places where the derivative does not exist. So I'm going to turn here. So the first place where we're not going to have a derivative is at a corner. And so anytime that we have, anytime we have an absolute value function, here we go. Okay, it will have a corner. Okay, so therefore there will always be one place where the derivative does not exist. So here we're talking at this point right here. That's what we call our corner. And we're going to see those when we have absolute values. So for example, here it says to find all points in the domain of f of x equals the absolute value of x minus 2 plus 3 where f is not differentiable. Now, I know that this graph is just the absolute value of x. This minus 2 means it's shifted to the right 2 and up 3. So if I were just to do a quick sketch of this graph, instead of that corner being at 0, 0, I know it's going right 2 and up 3. So it's going to look something like this. So again, I have this corner point here at x equals 3, x equals 2, so I would say that f of x is not differentiable at x equals 2 because of that corner point. And again, the idea that we have here, it's not differentiable, means the derivative does not exist at that point. Other places where we are not going to have a derivative is anywhere that we have a discontinuity, whether it's removable, infinite, jump, or oscillating. And we know we have to watch out for discontinuities whenever we have a piecewise function or a function that might have a vertical asymptote. Right, with our piecewise functions, we know we have to look out for those jump discontinuities. Vertical asymptotes, right, are going to give us those infinite discontinuities. So if I look at this function here, my piecewise, to find all the points in the domain of this function where f is not differentiable, I know I'm going to look out for this point x equals 3, because if it's piecewise, I'm wondering if maybe I have a jump there. So I'm going to see if this is continuous, first of all, at x equals 3. And just to review, we know to be continuous, the limit as x approaches f 3 from the left of f of x has to be equal as I approach 3 from the right, and that has to be equal to f of 3. So if I check 3 from the left, I have 3 minus 2 is 1. 3 from the right, 4 times 3 is 12. Right away I can see that my left and right hand limits are not the same, which means I am not going to be differentiable because I'm not even continuous. If I'm not continuous, I can't be differentiable. So I would say that f of x is discontinuous at x equals 3, right, because those limits are not the same. The limit as x approaches 3 from the left of f of x is not equal to the limit as x approaches 3 from the right of f of x. I have a jump discontinuity there. So therefore, and I apologize, I'm going to squeeze this in, therefore it is not differentiable. At x equals 3. And again, I apologize for cramming this in here. Okay, Now I also have a rational function here, and again it's asking me to find where that is not differentiable. Now I know when I have a rational function, I'm going to be looking out for any vertical asymptotes. So if I factor my denominator, I'm going to get, let's see, x minus 3 and x plus 1. So I know I'm going to have infinite discontinuities at x equals 3 and x equals negative 1. So I know that f of x is not differentiable at x equals negative 1 and 3 because of my vertical asymptotes. All right, so we're going to go on and look at a couple other places where our derivatives are not going to exist. So now we're going to look at this idea of a cusp. Okay. The idea here is anytime we have a function with a rational exponent, it's going to have a vertical tangent or a cusp. So again, there's going to be one place where the derivative does not exist. Okay, so now I can see the cusp here. If I were to look at this tangent closer and closer to 0, that's going to approach a vertical line, which is undefined. Same thing with here. If I look at x equals 0, I have a vertical tangent line, which is going to make me not differentiable. So here's where we have to look out. For example, find all the points in the domain of f of x equals x to the 1/3 where f is not differentiable. So I know that graph is going to look something like this. Right? We get that vertical tangent there. So we would say f of x is not differentiable at x equals 0 because of a vertical tangent. Oh, and you can't see that. Sorry about that. I'll scooch this over. Now, if I look at something like f of x equals x to the 2/3, now my graph looks a little bit different. It's going to look something like this, because of this even number up top. Now we would say we're still not differentiable, but now it's because of what we call a cusp. So those are the things, some of the things we'll have to look out graphically, is those vertical tangents, cusps, and corners. So now we're just going to spend some time going through the examples, first looking at graphs and determining where it is and is not differentiable, and then we're going to look at a couple functions to wrap this up. So let's turn to page 17 here. So our question asks to determine whether the function is differentiable or not at the given x values, and to explain why not. Okay. Oops, actually I'm up here. All right, so we're going to identify where a derivative does not exist and then explain why it does not exist. Kind of classify what's happening there. So the first thing I see happening is here at -2. And what it looks like to me is that I have a vertical asymptote here. So I would say I am not differentiable. The derivative does not exist at x equals -2. And I would say that's due to an infinite discontinuity. So anywhere I'm discontinuous, I'm also not going to be differentiable. The next issue I notice is right here. Okay, x equals -1. We would say we're not differentiable there. The derivative does not exist because of a cusp. Okay, moving along here, I can see that I'm going to have a vertical tangent. So at x equals 0, that derivative is not going to exist because of a vertical tangent. And then the last part I notice here as I'm going along is that x equals 2. I have a discontinuity, and I know that's a removable discontinuity, so I would not have a derivative at that point. So again, we just have to be able to pick out in graphs any issues that are going to cause a problem with the derivative. So for right now, we're not going to go through the rest of page 17. We'll use that to kind of review before we start the activity in class tomorrow. So let's keep going, and now I want to actually look at a couple of functions and see what we need to be able to do there. So for number 1, it says show that the following function has left-hand and right-hand derivatives at x equals 0, okay, but that there is no derivative there. Now remember, this is telling me if it has left-hand and right-hand derivatives, but there's no derivative defined there, it means that the left-hand derivative is not equal to the right-hand derivative. So we're going to see if we can show that that is the case. So the first thing I'm going to do is take the left-hand derivative here. So for my left-hand derivative, I know that's going to be the limit as x approaches. I'm looking at 0 here, so 0 from the left, I know is going to be x squared. So remember, I'm looking at f of x, which is x squared, minus f of 0, which is going to give me 0, over x minus 0. So now I can do some simplification. The limit as x approaches 0 from the left. Well, this just simplifies to x squared over x, which is just going to give me, let's go ahead and do that, over x is just equal to the limit as x approaches 0 from the left of x. So to evaluate that limit, I plug in, and I find out that my left-hand derivative is 0. Now let's look at the right-hand derivative. So I have the limit as x approaches 0 from the right now, which is obviously this function. So I have f of x, which is 2x, minus f of 0, well 2 times 0 is 0, over x minus 0. Now if I look at this one, this is just the limit as x approaches 0 from the right of 2x over x, which is just the limit as x approaches 0 from the right of 2, which gives me a value of 2. So clearly now my left-hand derivative is defined, my right-hand derivative is defined, but they're not equal. So we would say that y is not differentiable at x equals 0 because the left-hand derivative is not equal to the right-hand derivative. And this is the type of work you'll be doing in the first, I think, 4 problems in your homework tomorrow, is showing the left-hand derivative and the right-hand derivative, and either showing that they are or are not equal. So this will be good to go back to. I'm going to make a note when you're working through the 3.2 Day 1 worksheet, number 1 through 4. This is the work that I'll want you to show when you're talking about where those functions are not differentiable. All right, one last example, and then we're done for this video. Now I have another function. I have a piecewise function here. And so one thing that I actually should have done in the example above Whenever I have a piecewise function, I actually shouldn't jump right into finding the left-hand and right-hand derivative. We know that one of the things that can happen with our piecewise function is that we may not even be continuous there. And if there's any type of discontinuity, we're not differentiable. So actually the first thing I need to check with a piecewise function is check if you're continuous. Right? Because if it's not continuous, it's not going to be differentiable. Now it happens that the first one is continuous, so we're okay there. But we need to go ahead and check that first. So to check if I'm continuous, we know that we need to check the limit as x approaches 1 from the left of f of x. See how that compares to the limit as I approach 1 from the right. And then I need to check f of 1. So as I approach 1 from the left, I have 1 squared, which is 1. As I approach 1 from the right, I have 2 times 1, which is 2. So right now, we know we have a jump discontinuity there. So automatically now, if I'm not continuous, I can't be differentiable. So we would say that y is not differentiable at x equals 1 because there is a jump discontinuity. At x equals 1. So again, I got a little bit ahead of myself in the previous example, but that one happens to be continuous. But here we want to make sure we are checking whether it's continuous or not before we start jumping into derivatives. So tomorrow you'll have a chance to kind of work through all this in class, and I will see you then.